difficult questions for Brian and Noel, or by email preferably. Yeah, maybe I'll be able to handle it better that way. But yeah, as mentioned, this is some work that came out in GRL last month with colleagues at Lawrence Livermore. The motivation for this work stems from various previously published studies which showed that climatological biases in clouds or potentially their radiative properties might relate to future variability in global cloud feedback strength and thus climate sensitivity. So this dates back to the work of Volodin in 2008, shown on the right, basically linking the gradient in cloud fraction between the poles and the tropics, southern hemisphere and the tropics, to ECS strength. Trenberth and Fasulo also highlighted the relevance of southern hemisphere radiative properties to ECS, as shown in another one of these emergent constraint type plots on the bottom right. And then more recently, Seiler et al. 2018 showed that differences in cloud contributions to albedo in areas of warm versus cold SSTs were closely tied to global cloud feedback, or GCF, in CMIP5. However, many of the proposed emergent constraints on global cloud feedback and ECS over the years have struggled with what we term as out-of-sample testing, where a relationship is found to be absent in a new ensemble. In this work, we explore whether climatological metrics such as these are better suited to constraining regional rather than the more complex global cloud feedback. We looked at a variety of metrics, including shortwave, longwave cloud radiative effect at both the surface, top of atmosphere, total cloud cover metrics, and condensed water path metrics. For the sake of time here, I'll focus on two main metrics that we talked about in the paper. One being the gradient in climatological shortwave CRE between these warm and cool gradients, as shown in this map from Seiler's paper, basically from the areas shown in red to the areas shown in blue, which are the warm areas. The second is a zonal mean of the shortwave CRE across the southern hemisphere extratropics, which is somewhat inspired by a combination of Volodin and also Trenberth and Fasulo. And in this work, we crucially use model data from three phases of CMIP, so through CMIP 3 through 6. There's some slight differences in CMIP 3, whereby we can't calculate cloud feedback values the exact same way, but they do help to assess the robustness of an emergent constraint if you can find the same relationship, for instance. And to start, I'll show how the gradient in shortwave, or how the gradient in the shortwave CRE between these warm and cool SST regions correlates with zonal mean cloud feedback in CMIP5. So basically across latitude on the x-axis here, and then the cross-model correlation strength is shown on the y-axis. And so these two dots on the right basically just show the correlation for the between this metric and the tropical cloud feedback, and then the global cloud feedback on the right. And so we see in CMIP5, which is what Seiler built their emergent constraint on, there's a very strong relationship between this metric and the cloud feedback across most of the sort of 35 south to 30 north range. However, when we look at it out of sample in CMIP 3 and 6, there's a much weaker relationship, particularly in the tropics. And this is reflected in our correlation with the tropical and global cloud feedback on the right. Alternatively, we can do the same thing, but for the southern hemisphere extratropical shortwave CRE. And we find that it's closely related to cloud feedback across this 35 south to 20 north range, even more so with the exception of CMIP 6 as you go to higher latitudes. And in all cases, this drives a very strong relationship with the tropical cloud feedback. And because of the tropical clouds' importance to the global cloud variability, we see a strong relationship also with the global cloud feedback. And so on the version shown there, I was looking at specifically the 40 to 50 range for this zonal climatological metric. But we can see that really anywhere from 30 to 60 south, you have a fairly robust relationship across the ensembles. And we can also visualize this when we map the relationship between shortwave CRE at each grid cell and tropical cloud feedback. And so the consistent thing that we see across the generations is this strong anti-correlation in brown over the mid-latitude ocean basins. And the reason why the gradient metric struggles in CMIP 3 and 6, we can also infer from this figure. It's essentially just the absence of these blue / green colors in CMIP 3 and 6. So basically, you're not getting the same gradient strength as you were in CMIP 5 when it comes to this type of metric, which weakens the relationship with tropical cloud feedback. And so given the robustness of this gradient metric, or not the gradient, the zonal mean metric, we build an emergent constraint on the tropical cloud feedback. So basically our x-axis is a PI control measure of shortwave CRE, 40, 50 south in this case, and the y-axis is the tropical cloud feedback strength. And so we can add our different ensembles, so CMIP 6, CMIP 5, CMIP 3 as a sanity check, even though the tropical cloud feedback values are calculated slightly differently. And then we create a joint ensemble of CMIP 5 and 6 as our baseline to build this emergent constraint. So we can use observations from series and ERA5 reanalysis to put our model spread into context. And so on the right this is basically a 95% prediction interval of the whole CMIP 5 plus 6 data set. And then this is our emergent constraint 95% prediction interval using similar methods to what we've used before, basically this Bowman et al. 2018 paper. And so what this does is it suggests a tropical cloud feedback strength that's fairly similar to the model mean, a value of about 0.51, but it shows a significant reduction in model spread, about 34%. So I'll just note that the CMIP 3 data isn't used in the final constraint again because it lacks an abrupt 4 times CO2 scenario, even though in this case you could probably use it. And because the tropics are so important to variability in the global cloud feedback, a similar relationship will exist with the global cloud feedback. But obviously this is not, when you look at the global change, there are many more factors, much more complex. And so this is why, potentially one of the reasons why so many past studies have struggled in constraining, say, the global cloud feedback or ECS, is just that they were perhaps looking at something driven by a more regional process. And so if we apply the same thing, we can suggest a global cloud feedback value of around 0.4, but really the point here is to drive home this tropical cloud feedback constraint. We can also break down each region's individual contribution to the emergent constraint using this framework developed by Caldwell et al. And essentially the areas in brown are contributing more, the darker the brown, to the negative correlation that we see. In this case, between the zonal mean shortwave CRE in the extratropics and the global cloud feedback. And so the key here is that there's negative values predominantly located in the tropics, especially in low cloud regions off the west coast of South America, Africa, and Australia. But the importance of each region can differ slightly from one ensemble to the next. And this is mainly because I'm showing the relationship to the global cloud feedback, which if you notice on the past slide is not as strong as the relationship to the tropical cloud feedback. And so to better understand this relationship, we took the approach of grouping our 55 GCMs by their extratropical shortwave CRE values using the 10 largest and 10 smallest, or 10 most negative and least negative. And so here I'm plotting the difference between those two group means. And we see that there's significant discrepancy in cloud feedback across the tropics between these two groups, which is what we expect based on the relationship that we found. We also see that the group one models, ones with more negative shortwave CRE in the exotropics, have greater cloud coverage across this area and also seeping into the low cloud decks. And while we expect differences in shortwave CRE across the exotropics, because that's how we're defining the groups essentially, we see that this also extends into parts of tropical oceans. And as a side effect of that, this happens to coincide with cooler tropical SSTs, which favor greater low-level cloud formation. And so this is can be a bit of a chicken and egg problem. We show that similar shortwave CRE differences also exist in AMIP runs. And basically, since these, which implies that the SST anomalies are likely driven partly by the more negative shortwave CRE. So when you introduce coupling, this is basically a difference map in panel F between panel C and panel E, showing that coupling is what's increasing the shortwave CRE difference between these two groups of models. And so I think I'm low on time, last minute, so I'll quickly step through the mechanisms. But basically, this builds off prior work, which shows that through radiative perturbation experiments, extratropical energy biases can influence mean state tropical SSTs and clouds. Notably, this Kim et al. 2022 and some of Sarah Kang's work gives some suggestion of how this cooling can move from the extratropics equatorward. And in our work, we find that the cooler conditions help drive brighter mean state clouds in these group one models, as shown on the right here. And so when these brighter clouds are subject to future warming, which helps to promote the loss of low clouds, this therefore produces a stronger cloud feedback in this group of models. And so I think I'm out of time, but I'll leave this summary slide up. Essentially, we've just shown that climatological cloud properties can be used to robustly constrain regional cloud feedbacks. But note that finding these relationships is the first step to understanding them, and healthy skepticism should be maintained about this type of EC until it is fully understood and until the mechanisms are better flushed out. And I'll end there.
Great. Thanks, Chad. That was awesome.
Thanks.
So do folks have questions? You can either raise your hand or put the question into the chat or unmute yourself. I'll start off with a quick one, Chad. When you were defining tropical, was it based off of geography or based off of cloud type? Like, were you
Yeah.
lumping in some of the low clouds and the high clouds in the tropics?
Yeah. So it's I guess on this slide you can see it. Tropics essentially just base definition of 30 to 30. Rather than isolate for specific cloud types, which basically some work has shifted away from trying to constrain the global quantities to looking at either specific cloud regimes or regions. And one way to do that was look at it zonally. We took the approach of being flexible initially with how we tackled this problem. But when we saw the agreement across ensembles for such a large latitude band between these two metrics, that sort of shaped our approach going forward to just use the zonal mean, since it is the low cloud areas that are controlling much of the variability.
Cool. We have time for another question, and then we can continue the conversation in the chat.
They can also, if they missed my initial comment,
Yeah.
You
Looks
know,
like we have one
save the tricky
right
questions
here,
for
Chad.
Brian and
Yeah.
Noel.
So maybe this is
It's
a
not a
tricky
tricky
one.
one. It's a
Yeah.
very easy one. I got a bit lost with the abbreviations, but what is it again that you use as the predictor for the tropical cloud feedback?
Yeah, so it's shortwave CRE, cloud radiative effect, just the climatological value. You can define it either at the surface or top of atmosphere. We do both, but we find that the definition at the surface is slightly stronger.
Okay, that was the SFC.
Yeah, yeah.
Okay, yeah, thanks.
Yep. Cool.
Great. We should
Thanks.
probably move on to the
Yep.
next talk. Thanks, Chad. Shah, do you want to
Yeah,
introduce the next
thanks,
speaker?
Chad. Thanks, Chad, very much. So next we will have Noel Brizuela. And Noel is currently a postdoctoral researcher at Mount. So he's also ocean scientist. Also, we'll hear something from a different perspective about tropical thermocline helps power Pacific equatorial upwelling. It's all yours.
Thank you, Sha. Yeah, you can see my slides. All set,
Yeah,
right?
it looks good.
Okay, cool. So yeah, Sha said this is work that I've done in my postdoc that I'm wrapping up now. And the postdoc was focused on this hot topic that I think many of us are familiar with, the uncertain future of the tropical Pacific Ocean, that over the last few decades we've seen areas of cooling in the eastern equatorial Pacific and southeastern tropical Pacific. And there's great controversy about what's been driving those trends, as well as what might happen to the sea surface temperatures in those regions. Now, naturally, Pacific equatorial upwelling has emerged as a crucial player in that whole line of research. Upwelling, as you probably all know, exerts a tremendous influence on Earth's climate. It's coupled to the water circulation and cloud formation over the Pacific. So when I started working on this topic, I little by little started realizing that we don't, as a field, we don't really understand upwelling as well as I think we overestimate how well we understand upwelling. So hopefully I'll be able to get across to you what those shortcomings are, and I'll share as well my solution to understanding more of how this upwelling works. Now, say that you have model output and you want to understand or explain the spatiotemporal variations in upwelling in that model. A natural first step might be to go to the equations of motion. But if you do that, you will quickly be frustrated to find that you cannot use the equations of motion to explain vertical motion in an ocean model, because ocean models make the hydrostatic assumption, which leaves this equation here for vertical momentum. And the problem here is that W, the vertical velocity, has been removed from the momentum equations. So there's no way for us to get vertical motion from momentum conservation. So that's disappointing. And instead of the approach that I think we're all familiar with is using not conservation of momentum, but conservation of mass to explain vertical motion in the ocean. In the equatorial region, the idea here is that you have the trade winds blowing along the equator. They induce an Ekman outflow that goes meridionally away from the equator in the surface. And that wind also sets up a pressure gradient that drives a geostrophic inflow. So what we end up having is water goes out of the equatorial region on the top, it comes in the bottom. Therefore, there must be vertical upward currents in between those two layers. Now, that's perfectly sound physics. That is 100% correct. But conservation of mass has a few limitations. Most importantly, that it cannot tell us anything about cause and effect. And the way that plays out with equatorial upwelling is that we know that there must be upwelling, but we don't really know what is the force that is making water move upwards. And the way I like to say this is that we don't know if upwelling is being pulled from above by the divergent Ekman outflow, or if it's being pushed from below by the geostrophic inflow. So these, neither of these two approaches is going to tell us whether the upwelling is being pulled from above or pushed from below. And if we want to understand what's going to happen to equatorial upwelling in the future, we need to know whether the dominant influence is going to be from the equatorial push from below for the thermocline contribution, or the direct wind influence. So to work around this issue, I went to the third conservation law, which is conservation of energy. And here we used this framework of local available energetics from Remy to you. And the idea here is that we take the distribution of mass and the three-dimensional map of densities in the ocean, and we ask, given this distribution of mass, if we remove all forces from the ocean and let the ocean adjust itself to a state of balance, how much kinetic energy can we extract from each water parcel? So essentially, we're imagining rearrangement of fluid from the actual state of the ocean to a reference state where all the isopycnals are flat, and assigning and finding out how much kinetic energy we're going to extract from each water parcel. And the real advantage of this framework is that from the hydrostatic vertical momentum equation, we recover this term that now has a W, and we're going to call that the energetic cost of upwelling. It's the transfer between available and kinetic energies that happens when we move water vertically. So now we have W back in the equations, and we can estimate how much energy it takes to move water upwards in the equator. We applied this framework to output from CES-M2, and really here, well, this is what we get. On top is this energetic cost of upwelling, and the important point here is that the fact that there's this blue area where the energetic cost of upwelling is negative. This is an average between 3 south and 3 north. And the fact that this quantity is negative here is profoundly consequential. That is because a negative cost of upwelling means that vertical motion there implies a transfer from potential energy to kinetic energy. And winds cannot directly supply kinetic energy. Therefore, this fraction of the upwelling, the vertical motion here, must be powered by something other than the local winds, by some physical process in the ocean that supplies potential energy. And we find that this, the available potential energy that is necessary to explain upwelling in this part of the equatorial Pacific is that energy is being supplied by advection and by irreversible processes, including vertical mixing and parameterized eddies. So if you take these two blue blobs, add them up in your mind, they're going to look pretty much exactly like the blue area over in panel A. So that's nice. We know now that this part of the upwelling cannot be powered directly by winds. It is powered instead by the squeezing of the thermocline that's pushing water from below. But now we take a step back and ask, where is the thermocline getting that energy to move things upwards in the first place? Here I'm showing these, again, vertical integrals of the transfers between potential energy and kinetic energy. And really the most important piece of information here is panel A. Here we see production of potential energy by downward movement, by downwelling. So essentially, wherever the surface is really warm and the seawater has low density, when we have downwelling in those regions, we're putting low density water into the thermocline, and that will build up potential energy that then is held in the thermocline, because these water parcels have such low densities that they will want to come back up to the surface when they interact with the rest of the ocean. So we see that there's these two long sort of areas of potential energy generation that flank the equatorial region. And these are the near equatorial cells that have really high SSTs and that have permanent downwelling. And we also see that there's some additional potential energy production in the southern half of the northern subtropical gyre. So this whole area that is then connected to the equatorial region via the Mindanao West Boundary Current. So the idea then is potential energy is imparted onto the thermocline by the downwelling of low density waters in areas of high SSTs. That water, that low density water, is then advected to the equatorial region, where the energy is used to drive upwelling in the central and western Pacific Ocean. We see this usage of potential energy here by evidenced by the blue in panel B. And then if you think of a water parcel going along the equatorial current system, it's going to start its way over in the equatorial undercurrent here. It's going to rise slowly, eventually get to the eastern Pacific. And the second half, more or less, of that trajectory along the EUC, this water will now need to consume kinetic energy in order to keep rising. So by the time the cold water gets to the surface cold tongue, it is cold, and so it will have required kinetic energy input to get that close to the surface. And that's where the influence of winds and the local winds along the equator, that's where it comes in. So with this, we devise, or we explain, this near equatorial energy cycle, in which we begin with upwelling powered by potential energy. Then the rest of upwelling in number 2 is powered by kinetic energy. When the water gets to the cold tongue, it gets heated, so its density becomes lower, and that enables water to again generate potential energy when it downwells, and then the cycle continues. And an important implication of that is that now the buoyancy forcing in the equatorial region is going to determine the efficiency with which off-equatorial winds can drive equatorial upwelling. And to finish with, so if we have this new explanation for upwelling, it must be able to explain El Nino and La Nina. And fortunately, we see that it explains it well. So these are composites from CSM2 again, of the potential energy stored in the equatorial region during El Nino and La Nina months. And in the bottom, we see the supply of potential energy to those regions. So whenever we're in La Nina, we see an enhanced supply of potential energy to that region. And where we are in El Nino conditions, there is little potential energy production and storage in the thermocline. And so there is not that, the thermocline is not being squeezed as hard from below to drive upwelling. And this figure is a little convoluted in how to explain it, but essentially what this figure shows is that, so there's one choice of modeling that we do, right? When you do available energetics, you need to choose a reference density profile, and there is no universal way of how to choose that. When we test the sensitivity to that reference profile, we find that as we change that reference profile, and we calculate how much kinetic energy you need to put into the equatorial region to drive upwelling, the the burden of needing to supply kinetic energy switches between being in the equatorial region and the subtropical cells. This essentially just points to how the equatorial Pacific and the subtropical Pacific regions are energetically connected, and the energy that is spent to drive downwelling in the subtropical cells can then be recuperated by having that potential energy drive upwelling in the equatorial region. That's all I have. Thank you very much for your attention. And yeah, I'll take any questions.
Thanks, Noel. That was awesome. We'll see how
Thank
this
you.
is shaped up. Any questions for Noel? Feel free to unmute yourself or ask it in the chat.
Hi, I have a question. So maybe I'm understanding this poorly, but is perhaps a component of the intensity of upwelling in the cold SST and the cold tongue related to the rate that a water parcel is heated as it travels in this cycle?
Yeah, well, I think your question gets at something really important, that it takes more energy to lift a heavy water parcel than it does to lift a light water parcel. And so if I'm a water parcel that's going along the equatorial undercurrent and I'm being diabatically heated, so my density is becoming lower and lower, you might get to a point where you don't need any extra energy input, and just the heating of that water parcel is going to allow it to go upwards. And so that is what we're quantifying here. So this blue here is that diabatic heating and how it contributes to the upward motion. So I don't know if that completely answers your question.
So panel B is adiabatic, is what you're saying.
Yeah, okay, so panel B is adiabatic. I may have confused my words. So panel B is advection. Panel C is diabatic heating of the water parcels, and the influence of that diabatic heating on potential energy. Does that answer the question?
Yeah, I think so. Thank you.
Okay. Thanks.
Other questions for Noel? So Noel, this is a mean state understanding. I mean, you showed that it worked reasonably well for La Nina and so. Do you have a sense of what's going on seasonally? Since that's kind of like, there's such a huge asymmetry in the seasonal cycle in the tropics.
Right. I imagine in the seasonal cycle, we would see something similar to El Nino and La Nina, since the trade winds strengthen seasonally. We haven't gone through the numbers. Right now, what we're doing to look at higher frequency variability is looking at tropical instability waves, which are, intraseasonal frequencies. But definitely the seasonal cycle is something that we should look at.
Great. Thanks, Noel, one more time. And then Sha, we can move on to
Yeah.
the last speaker.
Thank you very
Right.
much.
Thanks, Noel. So we'll have our last but not least speaker today, Brian Rose. Brian is a professor currently at the University at Albany, and he will talk about how the low clouds and the Southern Ocean process could shape our understanding of transient climate sensitivity.
Okay, are we seeing my title slide?
Yeah, looks good.
Very good. All right, thank you, Shah, for the introduction. Thanks for having me here. I'm going to move something out of my way on my screen here. There we go. So I'm going to talk today about results that just came out in a paper hot off the press in Journal of Climate. The paper is led by Rob Ford, who's a PhD student working with me at Albany. Happy to say Rob's on the call today, so if I get hard questions, I can have Rob help me with the answers. And a former PhD student, Cameron Renkrell, who used to work with me at Albany, was also involved in this work. So we're going to talk about an idealized modeling study that confused us for quite a while, but I think we've managed to extract from it some interesting new insight into some links between things that are going on in the Southern Ocean and cloud feedbacks. So let me figure out how to advance my slide. All right, so I want to start with, broadly speaking, the problem that we're interested in here is pattern effects that govern transient warming of the climate system under CO2 forcing. And what I'm showing you on this slide is just a whole lot of snapshots of ocean heat uptake patterns. And these are actually extracted from CMIP, actually CMIP 5. These are patterns of anomalous heat uptake into the oceans in a bunch of different model simulations of 1% per year CO2 ramp, just snapshots taken at time of CO2 doubling. And the reason to put them all here is just to make two quick points. One, there are things that the models kind of agree about in broad strokes. The fact that, and this panel here shows the ensemble average across all of these models. The models tend to agree that there are sort of global hotspots of heat uptake under transient warming. One of them's here in the North Atlantic, and the other one is this broad band of heat uptake in the Southern Ocean. But there's also things, lots of details by which these models don't agree with each other, and it's kind of easiest to see in the line plots that show the zonal average, which we can see. Yes, the models agree that there's heat uptake in the North Atlantic and in the Southern Ocean, but they disagree on basically all the details. So we're kind of broadly interested in how these diversity of patterns that the ocean seems to impose on the rest of the climate system in these transient scenarios plays out in terms of radiative feedbacks. And a lens for studying this is actually to set up this abstraction that I'm going to tell you about now. So what we do is we produce a diversity of what I'd like to call hypothetical transient warming scenarios in a single model. And we do that by taking a model, it's the CESM in a slab ocean configuration. And then when we go into slab ocean configuration, the ocean heat uptake, these patterns I was just showing you become an input to the simulation. And so we take this single model and we run it through a number of these simulations where we double CO2 plus impose this pattern of heat uptake that we've diagnosed from some model that was in the CMIP archive. And so each time we do this, we run the model out to equilibrium. And so what we're actually modeling is the equilibrium response of the surface ocean and the atmosphere to the combined effect of the greenhouse gas forcing and the ocean heat uptake pattern. So we run it to equilibrium, but we're thinking of these as representing snapshots of hypothetical transient warming scenarios, just to give us an opportunity to investigate in a single model context how the patterns of ocean heat uptake impact the climate state. So what we get when we do this is a big diversity of climate states. And what I'm showing you here, it's a busy slide. There's a big set of postage stamps here that all represent these are surface air temperature. These are warming patterns in each one of these simulations with the same model, right? So the labels here now represent the heat uptake pattern that we diagnosed from a CMIP model and then imposed in our CESM simulations. If we do just the CO2, that's this bottom panel. I hope you can see the mouse that I'm moving around. we put the CO2 only in the model. Of course, we get a familiar looking sort of polar amplified warming pattern. But when we do the CO2 plus the ocean heat uptake, we get this whole diversity of things that look sort of like transient warming states that, for example, many of which show this lack of warming or even a little bit of cooling around the Southern Ocean. Okay, we average them all together. We get this map here, so this strongly Arctic amplified pattern. And okay, I'm showing you the sea ice change here. So we get lots of loss of sea ice in the Arctic and very little change in the ensemble mean in the Antarctic. Okay. There are a few members of this group of simulations that go a little bit haywire, and that's actually a little bit interesting. There's a couple of cases where, for reasons we don't think are particularly physical, the slab ocean model with the sea ice sitting on top of it gets kicked into a state where there's substantial growth of sea ice around Antarctica in the presence of this doubled CO2. So we're going to take those cases out of the ensemble, and we're going to hold them aside and use them to sort of as a kind of out of sample check later on in the talk. So I guess for the rest of the talk, when I talk about the ensemble, I'm talking about the rest of the cases that don't experience this fairly substantial ice growth around Antarctica. Okay, so what we wanted to do was some feedback analysis to gain some insight into the pattern effects that arise in this one model that produces this diversity of warming patterns, and learn something, if we can, about the causality. So we apply radiative kernels, and there's lots of things potentially to see here, but I want to draw your attention to what I think are the key lessons. Oh, okay. So what we're seeing in this figure are terms in the radiative feedback analysis that we get out of the kernel method, and for each of these sort of columns, I'm showing you with the X is the analysis on the model case that was run with CO2 forcing only, so our sort of snapshot of equilibrium warming. And then the bar represents the range of our ensemble of our hypothetical transients. And key lessons here. So one thing I'd like to draw attention to is the fact that if we look here, this is the shortwave cloud feedback part of this analysis. That's what SWC is referring to here. This X, first of all, is very far outside of the range spanned by the bar. What that means is that under CO2 forcing alone, the global shortwave cloud feedback is substantially more positive than any of our cases that represent these hypothetical transient states. Okay. Furthermore, the shortwave cloud feedback itself is kind of the main source of spread in this set of hypothetical transient states. Okay, so I'm drawing a circle around the shortwave cloud feedback because it's the most interesting thing here. If we go over here, we see the total feedback, the sum of all feedbacks, and it's basically the same story, right? The CO2 is outside of the range spanned by our transient states, but this big sort of range spanned by this bar is mostly a result of the differences in shortwave cloud feedback across this ensemble. So I want to look a little bit at the spatial structure of those feedbacks to see what part of the world is giving rise to that signal. And the answer actually is fairly clear. It's the southern mid-latitudes. So we're looking at plots now of the zonal average of the feedbacks that we got from those kernels. And it really is here where we see this big spread across this spaghetti of lines in terms of the magnitude of the feedback in the region of the Southern Hemisphere storm track. The red line here is our CO2 only case. So again, the red line shows us that particularly in the southern mid-latitudes, this sort of equilibrium warming pattern that we get with CO2 alone produces a very, very different cloud feedback than our transients. And our transients span a very wide range of potentially and substantially more negative feedbacks. So what's going on? What is it about the clouds that's giving rise to those feedbacks? We focused quite a bit of attention, as indicated by the boxes on this map here, on two regions that seem to be particularly interesting. What we call the East Pacific Triangle here, and then the southern mid-latitudes in this big black box. What you're seeing in the panel is just in the ensemble mean, the change in low cloud cover, which turns out to be a pretty useful proxy for what's giving rise to those feedbacks that I just showed you. And so in this zonal average plot, we see the spaghetti, and we see again this property that the clouds are going in completely the opposite direction in the sort of equilibrium CO2 only case versus all of our hypothetical transients. And these, of course, have a big spread across them. I'm also showing here, when you see this plus delta SIC, that's a code here for those sort of out of sample cases that experienced substantial ice growth around Antarctica. Just to sort of point out that the same patterns are showing up here, just in a more extreme way. So it turns out that, thanks for that link, Brian Mapes. When we look, what we're doing here is we're just in sort of scatter plot style, we're looking for correlations between the cloud changes themselves in particular regions, that's on the x-axis of these plots, and the global mean surface temperature, that's the y-axis. So in a sense, thinking of the change in cloud cover in one or other of these boxes as being a predictor for global mean temperature. And lo and behold, it turns out that these southern mid-latitude clouds are very strongly correlated with that global mean temperature, and we're trying to interpret that through a causal lens, although it's of course a bit complicated as always. It turns out that the East Pacific Triangle is substantially less correlated with global mean temperature. And so we don't get a clear story, although the low clouds are changing a lot in that box in the ensemble mean. The spread across the ensemble is not something that, well, it's not correlated with the spread across the ensemble in the global warming that we get. So we spent some time looking at things like cloud controlling factors to try to wrap our heads around what are the relevant mechanisms here. So what these represent. So this is stability in this panel here. This is downwelling rates. This is surface wind speed in the bottom panel here, and then sea surface temperature. So there's some things that emerge out of this. The sea surface temperature, the stability, and the surface wind speed all show up as being important. I think that coming up with a very clear causal story here is not straightforward because of because of some complicated cause and effect between the clouds and the SST and the stability and so on. But this result in particular, the correlation with the surface wind speed, and I'll point out while I'm here, we put the pure CO2 case again on these plots just to show that although the clouds are doing something completely different in the pure CO2 case, they seem to line up very nicely with what we get with our ensemble of hypothetical transients, suggesting some consistency of mechanism that's operating in this model. This got us thinking about atmospheric circulation, right? And the extent to which the circulation of the atmosphere is sort of driving the clouds, which in turn might be driving the climate one way or another. And so the last thing that we looked at here is measures of storm track activity. So I'm showing you differences in eddy kinetic energy. And so in particular, in this black box in the southern mid-latitudes, in the ensemble mean, we have some spinning up of the storm track with this red shading. That's really what that looks like. Again, in the zonal average plot, we're looking at the spread across our ensemble of simulations and comparing it to the red curve, which is the pure CO2 case. And it kind of looks a lot like the clouds in the sense that this in the pure CO2 case, the storm track is weakening. In our transient cases, the storm track is strengthening, and the diversity of the strengthening that we are seeing here is strongly correlated with the diversity of cloud responses, and that's what's shown in this scatter plot on the right. So this is my attempt to wrap this up into a story. I think we're putting together a plausibility argument for a mechanism here. I think there's plenty more work to be done to nail down each link in the causal chain. But I think we're looking at what I think of as a positive mid-latitude baroclinicity cloud feedback. What I mean by that is cases across our model ensemble that experience more cooling or lack of warming around Antarctica under this CO2-driven warming experience enhanced baroclinicity across the southern hemisphere, which in turn results in a stronger storm track, which in turn is associated with greater mid-latitude low cloud cover. And those low clouds, it seems, are playing a very important role in kind of setting the global mean albedo and actually determining whether the planet as a whole is cooler or warmer. And so these cases that have the most cooling or the least warming around Antarctica end up being the cases that have sort of the weakest apparent transient climate response. So that's a bit of a whirlwind. And of course, all the details are in the paper. But to summarize, we generated this single model ensemble that I'm calling hypothetical transient warming scenarios, because we diagnosed heat uptake patterns from CMIP, and we put them all into one model and just sort of looked at what the model did in response to that diversity of heat uptake patterns. And what we got was a large spread in Antarctic sea ice and a large spread in global mean temperature. The spread in the global response was attributed to the shortwave cloud feedback in the southern mid-latitudes. That was the most important source of difference across our ensemble. And we've inferred that these clouds are actually remotely shaped by some teleconnections to the Antarctic sea ice and the SSTs in the more polar regions of the Southern Ocean via a few different mechanisms, I think, modulations of stability, but the baroclinicity is the argument I've emphasized here of that mid-latitude storm track. So it's an idealized study, but it does suggest that trends in Antarctic sea ice may play an underappreciated role in actually setting, remotely determining the cloud cover and thus the planetary albedo through this link between the atmospheric circulation and the clouds. So I'll stop there and take questions and hopefully get a chance to introduce Rob, who's here on the call, who led the paper. I'll just call Rob to introduce yourself right now. How about that?
Sure. Yeah, sorry, I had to turn on my camera. Hello. Yep.
Rob Ford.
Cool. Thanks for the great presentation, Brian. Rob for leading the work. Tony, do you want to ask your question?
Sure, thank you. Very nice presentation. I just want to go back to the previous slide that describes the feedback. And I guess my question is, if we started with greater mid-latitude cloud cover, could we make the case that that's driving the other two mechanisms that are described there?
So not entirely, I think, is my answer, right? Because I think the argument we're trying to make is that the subpolar regions of the Southern Ocean are important here, right? Because they're kind of determining what's on the cold side of the hemisphere. And so if we just come along and say, well, the mid-latitudes are cloudier, sure, we'll cool off the mid-latitudes, but is that enough to sort of set in motion this set of processes that require a stronger or a modulation of the storm track intensity? So my way of thinking about this is that we kind of need the sea ice to be involved here, because that's how, again, that's how we set up this sort of hemispheric scale temperature gradient that seems to be relevant.
Yeah, I guess in principle, it would be testable because you could devise a similar set of experiments where you're prescribing the perturbations from cloud cover.
Yes, one could do that. The other thing one can do, of course, is cloud locking, right? So if this argument that we're making here is at all correct, then if you did the same set of simulations with cloud locking, you would get a much weaker kind of range of responses, right? You find, okay, maybe I'll set up a bunch of cases that have more or less or a diversity of ice and SST pattern in the Southern Ocean, but the clouds won't have the ability to respond, and as a result, our sort of range of estimates of transient climate response would be much reduced.
Thank you.
Yeah, thanks for the question.
Awesome. And we're coming right up at the hour, so if folks want to hang on and maybe ask questions or whatever, that could happen. But otherwise, let's thank our three speakers again, Chad, Noel, and Brian. And thanks, folks, for coming to the 40th virtual ECS and Cloud Feedback Symposium.
Yeah, thanks everyone. We'll see you. Thanks all the speakers, and we'll see you next month. Take care.
Thanks a lot, organizers.
Thanks.